1,000 watt-hours per kilogram, a lifespan of 200 years, and 98% efficiency. This is no longer a laboratory fantasy. Graphene-aluminum-ion is breaking the limits of modern battery technology. It's lighter, more durable, more powerful, and it could completely reshape the future of transportation. So what makes it the next energy revolution? Before we begin, please help us reach 9,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. Why is graphene-aluminum-ion battery considered the future of battery technology? Electric vehicle technology today relies heavily on advancements in battery technology. While lithium-ion batteries dominate the market thanks to their high energy density, they still have many drawbacks. Slow charging speeds, risks of overheating and fire, limited lifespan, and dependence on expensive materials like lithium, cobalt, and nickel. Against this backdrop, graphene-aluminum-ion batteries developed by Graphene Manufacturing Group in Australia, in collaboration with the University of Queensland, have emerged as a revolutionary alternative. Using an aluminum anode, graphene cathode, and liquid ionic electrolyte, this technology promises ultra-fast charging, high safety, superior durability, and significantly lower costs. One of the most remarkable features of G+AI batteries is their extremely high power density up to 7,000 watts per kilogram, which is 10 times higher than conventional lithium-ion batteries' 250 to 700 watts per kilogram. This allows unprecedented charging speeds. In coin cell tests, charging times can be measured in minutes. If this speed can be scaled to automotive battery levels, it could fully charge an electric vehicle in just 10 to 15 minutes, something current lithium batteries cannot achieve. This could completely transform charging habits and the structure of global public charging networks. In addition, G+AI batteries demonstrate impressive thermal management. While lithium-ion batteries can reach over 60 degrees Celsius under high discharge rates, 20 C, G+AI batteries only fluctuate between 29 to 31 degrees Celsius under the same conditions. This means that active cooling systems, which typically account for 15 to 20% of an EV battery pack's weight, are unnecessary. Removing these systems can reduce total battery pack weight by 50 to 80 kilograms, improving driving range and overall energy efficiency. Furthermore, less heat generation increases both the longevity and safety of the vehicle and its passengers. Regarding lifespan, G+AI batteries show outstanding performance, withstanding over 2,000 charge-discharge cycles without significant capacity loss. This level can power vehicles for more than 1 million kilometers, 2 to 3 times longer than many current lithium batteries. Moreover, because they use aluminum and graphene, two materials that are not easily flammable, combined with a stable liquid ionic electrolyte, G+AI batteries have a very high resistance to thermal runaway, making fire incidents nearly impossible. This is especially important given recent consumer concerns following multiple electric vehicle fires caused by lithium-ion batteries. However, at present, the energy density of G+AI batteries remains lower than that of premium lithium batteries. Current data shows G+AI batteries at about 150 to 160 watt-hours per kilogram, whereas Tesla's 2170 cells reach up to 260 watt-hours per kilogram. Nonetheless, this is not the absolute limit. Many studies indicate that aluminum-ion batteries could reach up to 1,060 watt-hours per kilogram if design, materials, and manufacturing processes are optimized. This is part of GMG's long-term improvement plan. Currently, the technology prioritizes fast charging, safety, and durability before enhancing energy density. A major step forward is GMG's successful development of pouch cells with capacities over 1,000 milliamp hours, a crucial transition from laboratory coin cells to automotive-grade batteries. These cells are undergoing third-party testing to verify performance, stability, and scalability. Once this phase is passed, GMG plans to build a pilot production line aimed at commercialization. The basic structure of G+AI batteries is also similar to lithium-ion batteries, consisting of an aluminum anode, a graphene cathode, a liquid ionic electrolyte such as AlCl3 mixed with urea or EMIMCl, and a polymer separator. This design allows GMG to leverage existing battery manufacturing technologies, reducing plant investment costs and increasing production scalability. The unique aspect lies in how graphene interacts with trivalent aluminum ions, Al3+, enabling faster ion exchange rates and greater structural stability during charge-discharge cycles. Of course, many challenges remain to be overcome. First is the quality and cost of graphene. This material must achieve high purity and a perfect crystal structure to fully realize its potential. GMG has developed a proprietary graphene production method, but costs still need to be reduced for mass market application. Next is the issue of low voltage. Each G+AI cell has a voltage of about 1.7 volts, much lower than lithium-ion cells, so more cells are required to reach the same voltage level in a battery pack. This demands redesigning the battery management system and module structure. Despite these technical challenges, the advantages offered by G+AI will significantly impact the design and operation of electric vehicles in the future. With ultra-fast charging speeds, G+AI battery systems could enable electric vehicles to compete directly with the refueling times of traditional gasoline cars. By eliminating the active cooling system, the battery pack's weight and cost will decrease, while additional volume can be allocated to designing a more spacious passenger cabin. Most importantly, superior durability allows electric vehicles to use the same battery throughout their lifespan without replacement, significantly reducing maintenance costs and electronic waste. According to the plan, GMG is accelerating research and production, dividing development into sprint phases. Each testing period lasting several weeks with multiple variations in components, electrode thickness, solvent types, and assembly processes. The goal is to quickly optimize each step to maximize performance. It is expected that during 2025 to 2026, GMG will build a pilot production plant and begin assembling battery modules into electric vehicles such as motorcycles, e-bikes, or HVAC devices, before moving on to cars. In the market context, G+AI batteries could reshape the entire electric vehicle value chain. The absence of lithium, cobalt, or nickel will reduce pressure on supply chains of these scarce materials, currently dominated by China. Instead, aluminum and graphene are abundant, recyclable, and environmentally friendly. Additionally, G+AI batteries open new opportunities in personal air vehicles, eVTOL, humanoid robots, industrial drones, and other fields requiring fast charging, thanks to their high power density and heat-free durability. Although current energy density remains modest, and mass production capability still needs to be proven, Graphene-aluminum-ion technology shows great potential to replace traditional lithium-ion batteries. With advantages in fast charging, safety, longevity, ease of manufacturing, and environmental friendliness, G+AI batteries could become the foundation for the next generation of electric vehicles, not only faster but also cheaper, cleaner, and more durable. This is not just a technological advancement, but a major leap forward, bringing the electric vehicle industry closer to global adoption. Once again, please help us reach 9,000 subscribers. This is important for us to stay motivated. Thank you. Which technology is used to produce graphene in this battery? At the heart of G+AI battery production is the use of graphene, a single layer of carbon atoms arranged in a hexagonal lattice, combined with aluminum ions as the charge carriers. Unlike lithium, aluminum is abundant, inexpensive, and environmentally friendly, which substantially reduces raw material costs. However, producing high-quality graphene at scale remains a key challenge that manufacturers are actively addressing. Companies like GMG have developed proprietary methods to synthesize graphene efficiently and with high purity. This involves chemical vapor deposition or exfoliation techniques that produce graphene sheets suitable for battery electrodes. GMG's proprietary approach focuses on reducing production costs while maintaining the material's superior electrical conductivity and mechanical strength. The battery cells themselves are typically assembled in a pouch cell format, which is flexible, lightweight, and easier to produce compared to rigid cylindrical or prismatic cells. GMG's current research focuses on producing pouch cells with capacities exceeding 1,000 milliamp hours, aiming to balance energy density with rapid charge-discharge capabilities. One crucial step in manufacturing is electrode fabrication. The graphene-aluminum-ion battery uses graphene-based cathodes and aluminum anodes. These electrodes require precise layering and binding processes to ensure optimal ionic transport and mechanical stability. Advanced coating technologies apply thin films of graphene onto conductive substrates, maximizing surface area and electrical contact. The electrolyte used in G+AI batteries is another innovative aspect. It typically consists of an aluminum-ion conducting solution that supports fast ion movement while maintaining chemical stability. The electrolyte's compatibility with both the graphene cathode and aluminum anode is essential to achieving the battery's high charging speeds and longevity. Quality control during production is stringent. Each batch of cells undergoes rigorous testing to verify consistency, safety, and performance. Independent laboratories often conduct these tests to provide unbiased evaluations. Parameters such as charge, discharge efficiency, cycle life, capacity retention, and thermal stability are measured to ensure the battery meets industry standards. Scaling up production from the lab-scale prototypes to commercial volumes requires investment in automated assembly lines, clean room environments, and supply chain logistics. GMG and similar companies are currently expanding pilot production facilities and preparing for large-scale manufacturing. This phase involves optimizing process parameters to reduce defects, improve yield, and lower production time. One of the major advantages of G+AI battery production is its environmental friendliness. Unlike lithium-ion battery manufacturing, which involves mining rare and sometimes toxic metals like cobalt and nickel, aluminum and graphene sourcing is more sustainable and less harmful. Moreover, the manufacturing process consumes less energy and produces fewer emissions. Ultimately, the goal of producing graphene-aluminum-ion batteries at scale is to enable a new generation of electric vehicles, portable electronics, and energy storage solutions that charge faster, last longer, and cost less. By overcoming current production challenges and ramping up capacity, companies like GMG are poised to revolutionize the battery industry and accelerate the global transition to clean energy technologies. How will graphene-aluminum-ion batteries affect the cost of electric vehicles? Graphene-aluminum-ion batteries are considered one of the most promising battery technologies because they can significantly reduce production costs compared to traditional lithium-ion batteries. The main raw material of this battery is aluminum, a very common and inexpensive metal, unlike the costly and rare material used in current batteries. This greatly lowers the input costs for battery manufacturing. In addition, graphene, a very advanced material, although previously expensive, has seen production costs decrease with advancing technology. This means that with mass production, G+AI batteries will become much more affordable. The battery manufacturing process is also simpler and more environmentally friendly, saving electricity and reducing waste during production. Researchers continuously optimize this process to improve efficiency and cut costs. Compared to current lithium-ion batteries priced around $120 to $150 per kilowatt-hour, graphene-aluminum-ion batteries could reduce costs by 20 to 40%. In the race to develop safer and more durable batteries, low self-discharge capability is a key factor. Water-in-polymer salt electrolyte has emerged as a promising solution for organic batteries. By retaining up to 99% of energy each month, WiPSE prevents battery drain even during long periods of inactivity. So what gives it this outstanding advantage? Before we begin, please help us reach 8,700 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. How does the water-in-polymer salt electrolyte enable slow self-discharge in organic batteries? The biggest barrier preventing organic batteries from being widely applied is the rapid self-discharge phenomenon, meaning the quick voltage drop while the battery is not in use. In organic batteries using traditional aqueous electrolytes, free water tends to diffuse and react with electrode materials, leading to charge loss and damage to molecular structures. Recent studies have shown that organic batteries with aqueous electrolytes lose up to 30 to 40% of their voltage after just a few hours when left at open circuit. This makes devices using such batteries unstable, unable to store charge for long periods, and very difficult to commercialize. This is also why most previous studies, despite achieving good capacity, either do not publish or deliberately ignore the self-discharge rate, a serious but rarely mentioned problem. However, a breakthrough came with the invention of a new electrolyte called Water-in-polymer salt electrolyte, developed by a research team at Chalmers University of Technology, Sweden. The uniqueness of WiPSE lies in its chemical mechanism and material structure. Instead of allowing free water to exist in the electrolyte solution, the researchers used a supramolecular polymer network to trap water molecules in hydration cages. There, salt ions at very high concentrations, the molar ratio of salt to water far exceeds that of conventional solutions, are organized within a porous polymer structure, minimizing free water diffusion and thereby significantly reducing charge leakage currents. This mechanism not only limits water contact with the electrode surface, but also maintains the necessary ion transport for the charge-discharge process. Water in WiPSE still acts as an ion-conducting medium, allowing ion flow from the cathode to the anode, but it is anchored by the polymer network and sulfonate ions, preventing free contact or side reactions with the electrodes. This is considered a unique water confinement system that stabilizes the chemical and electrochemical properties of organic batteries. Experiments show that batteries using WiPSE maintain voltage for 7 continuous days without recharging, while batteries with traditional aqueous electrolytes lose almost all their voltage after just 10 hours. The self-discharge reduction exceeds 80%, opening unprecedented potential for long-term storage in organic batteries. Physically and chemically, the polymer network in WiPSE creates a stable environment for sulfonate salt ions with a high ion density, comparable to an ion supersaturation state, boosting ionic conductivity to about 1 millisiemens per centimeter. This porous and tightly bonded structure also prevents free water diffusion, minimizing electrode decomposition reactions that cause energy loss. At the same time, WiPSE maintains a wide electrochemical voltage window of about 1.8 volts, significantly higher than conventional aqueous electrolytes, which only reach about 1.0 to 1.2 volts, providing stable performance and safe operation. Additionally, the confinement of water within the polymer network greatly reduces evaporation and temperature fluctuations inside the battery, helping maintain electrolyte structural stability under real operating conditions ranging from 20 to 70 degrees Celsius. This significantly improves the battery's lifespan and performance in automotive or mobile devices that require long-term stability. Another advantage of WiPSE is its design flexibility. This electrolyte can be formed into gels or thin films, enabling applications in thin, flexible, or directly printed organic batteries using electrodes such as polythiophene, polyanthraquinone, or lignin. Tests combining WiPSE with these organic electrodes show capacity retention over 1,000 cycles without significant degradation, compared to batteries using traditional aqueous electrolytes, which only retain about 200 cycles before capacity drops by more than half. Finally, WiPSE not only delivers outstanding performance, but is also environmentally friendly and easy to manufacture at low cost. Its main components such as sulfonate salts, polyethylene glycol, and hydrocarbon-based polymers can be synthesized at low temperatures without toxic solvents and are biodegradable after their life cycle. This helps reduce environmental pollution compared to current organic electrolytes and opens a sustainable development path for organic batteries in the future. Once again, please help us reach 8,700 subscribers. This is important for us to stay motivated. Thank you. How does WiPSE contribute to making EV batteries lighter, more compact, and high-performing? The battery is the heart of every electric vehicle, and it is also the heaviest part of the car. For a popular model like the Tesla Model Y, the battery pack can account for nearly 1/4 of the vehicle's total weight, approximately 480 to 500 kilograms. This weight affects both the vehicle's performance and increases production costs and energy consumption. Therefore, Engineers and researchers continuously seek to optimize battery design to reduce weight, enhance efficiency, and simultaneously ensure safety. Among the most outstanding emerging technologies, water-in-polymer salt electrolyte, or WiPSE, is receiving special attention. Instead of using the liquid organic electrolytes typical of traditional lithium-ion batteries, which are quite heavy, flammable, and carry the risk of fire or explosion, WiPSE uses an electrolyte mainly composed of water tightly held within a polymer network. This brings two major benefits: significantly reduced weight and markedly improved safety. Water is non-flammable and also helps eliminate the toxic solvents commonly found in current batteries. A notable point is that WiPSE can reduce the battery pack weight by 50 to 70 kilograms compared to conventional lithium-ion batteries. While this number may seem small relative to a 2-ton vehicle, every kilogram reduced helps improve operational efficiency, decrease suspension wear, enhance acceleration, and lower energy consumption. This is particularly important for models like the Tesla Model Y, which users expect to have long driving ranges and smooth driving experiences. Not only lighter, WiPSE also allows the battery components to be designed closer together. In this case, lithium ions have a shorter distance to travel during charging and discharging, reducing resistance and increasing electrical conductivity efficiency. As a result, the battery's energy density increases significantly, potentially reaching 350 to 400 watt-hours per kilogram, 15 to 20% higher than traditional batteries. Therefore, electric vehicles using WiPSE batteries can travel longer distances without increasing the size or weight of the battery pack. Regarding charging speed, WiPSE enables batteries to withstand fast charging up to 3C, meaning a full charge can be completed in about 20 minutes, much faster than traditional lithium-ion batteries that currently handle only about 1 to 1.5 C. This is a significant improvement, saving users time and increasing convenience for electric vehicles on long trips or when quick recharging is needed. Safety is an indispensable factor. WiPSE, with its primarily water-based composition, reduces the risk of fire or explosion when the battery is impacted or malfunctions. This not only protects users, but also allows for thinner protective layers around the battery, further reducing weight and cost. At the same time, WiPSE is less prone to electrolyte leakage, which is a common cause of damage or short circuits in current battery types. Of course, WiPSE still faces several challenges. One of them is how to maintain a stable amount of water in the polymer during high-temperature operation to avoid evaporation that would reduce performance. Research teams are developing new polymers with better water retention and enhanced mechanical strength. Additionally, the vehicle's thermal management system plays a critical role in maintaining stable operating temperatures for WiPSE batteries. The electrochemical compatibility between WiPSE and electrode materials is also emphasized. Without optimization, side reactions may occur, affecting battery lifespan and performance. However, according to multiple research reports, WiPSE batteries can retain over 80% capacity after more than 1,500 charge-discharge cycles, outperforming many lithium-ion batteries currently on the market. Moreover, WiPSE technology contributes to reducing environmental impact throughout the battery's production and disposal cycle. Limiting the use of toxic organic solvents is not only safer for workers, but also reduces pollution risks when batteries are discarded. This is an important step toward the sustainable development goals of the electric vehicle industry. For Tesla, applying WiPSE not only improves the performance of the Model Y, but also strengthens its pioneering position in electric vehicle battery technology. Tesla is already famous for many innovations such as the cell-to-pack design to increase battery density, or the GigaPress, a large casting machine that reduces parts and vehicle weight. WiPSE will be a perfect addition for Tesla to continue lowering battery weight, enhancing safety, and expanding vehicle design possibilities. WiPSE offers many great benefits: weight reduction, increased energy density, improved design flexibility, enhanced safety and battery lifespan, and greater environmental friendliness. Although technical challenges remain ahead, it is clearly one of the promising technologies that could usher in a new era for electric vehicle batteries. Then, models like the Tesla Model Y will become lighter, drive farther, charge faster, and be safer. making the transition to electric vehicles not only a trend, but also a great sustainable experience for users. How does low self-discharge impact battery safety? The water-in-polymer salt electrolyte is considered a significant advancement in enhancing the safety of organic batteries, especially for electric vehicle applications. Traditional lithium-ion batteries use liquid organic electrolytes, which are flammable and have a flash point around 120 degrees Celsius, posing a high risk of fire and explosion in the event of a malfunction. Statistics show that over 100 electric vehicle battery fires have been recorded in just the past 5 years, with most incidents linked to liquid electrolytes. In contrast, WiPSE mainly consists of water, which has a flash point above 100 degrees Celsius and is inherently non-flammable. WiPSE also reduces self-discharge to below 1% per month, much lower than traditional lithium-ion batteries, which can experience 3 to 5% monthly self-discharge. This improvement not only extends battery lifespan to over 2,000 charge-discharge cycles, double that of many current batteries, but also lowers the risk of heat generation and explosion during long-term storage. Additionally, the WiPSE electrolyte avoids the common leakage issues found in traditional batteries, which often cause short circuits and damage. Upon decomposition, WiPSE does not emit toxic gases like hydrofluoric acid or flammable gases such as ethylene, thus minimizing hazards to users and the environment. Compared to solid electrolytes, WiPSE enables ion transport that is 5 times faster due to water's facilitation within the structure. Manufacturing costs for WiPSE are also estimated to be 20 to 30% lower than those for solid electrolytes, owing to simpler production processes and more readily available materials. However, the boiling point of water in WiPSE is about 100 degrees Celsius, which can lead to evaporation when the battery operates at high temperatures above 60 to 70 degrees Celsius during fast charging or continuous use. These temperatures are common in many electric vehicles today, so developing polymers that better retain water and implementing specialized cooling systems are essential. Laboratory tests have shown that new polymers can retain up to 95% of their water content after 1,000 hours at 80 degrees Celsius, helping to prolong battery life and stabilize performance. Compatibility between WiPSE and electrode materials is also carefully studied to minimize side reactions, maintaining over 90% efficiency after 1,000 charge-discharge cycles. Electric vehicle batteries typically operate across a temperature range from -20 degrees Celsius to 60 degrees Celsius, enduring vibrations and shocks during use. Traditional batteries usually degrade below 70% capacity after 1,000 to 1,500 cycles, reducing driving range and safety. WiPSE's water retention and stable polymer structure help limit capacity fade, maintaining over 80% capacity after 2,000 cycles, equivalent to more than 8 years of typical electric vehicle usage. Its very low self-discharge rate, under 1% monthly, reduces energy loss during periods of inactivity, extending storage time and lowering maintenance costs. Still, temperature management remains a major challenge. Modern fast charging can heat batteries above 70 degrees Celsius, causing water evaporation and electrolyte degradation. Effective cooling systems that maintain temperatures below 40 degrees Celsius can extend battery life by 25 to 30% compared to uncontrolled operation. Research also shows that the electrochemical compatibility of WiPSE with lithium electrodes can achieve over 99% ion storage efficiency, minimizing side reactions and preserving electrode structure stability over many cycles. Therefore, WiPSE not only represents a major leap forward in safety, but also promises significantly longer battery lifespan under harsh operating conditions. Successful advances in polymer development, thermal management, and electrode optimization will enable future electric vehicles to become safer, more durable, and more cost-effective. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.